Project 3.2.1, CHUMP, Clock Encounter by Atticus Stiplady. This is the first video in a short video series documenting the creation of the ACES CHUMP, which stands for Cheap, Homebrew, Understandable, Minimal Processor. The purpose of this specific portion of this project is to create the function and clock encounter of the CHUMP project. The clock is a tool that serves as a timing mechanism that synchronizes the operations of the processor. It includes 3 555 timers, 2 NAND chips, and various other parts such as a slide switch and various LEDs. The program counter in a CHUMP tracks the address of the next instruction, incrementing after each instruction to ensure sequential execution of the program. The clock encounter can be broken up into 2 parts, starting with the clock. The fundamental aspect of the CHUMP clock has to do with the 555 timers, specifically the 3 iterations of it, with that being the astable, monostable, and bistable 555. Each of these iterations of the 555 timer are vital in the creation of the CHUMP program counter and clock, and all build off the fundamental concepts learned in other projects, specifically Project 2.2, the 555 time machine. Going from left to right, starting with the astable 555, it is wired in such a way identical to Project 2.2, and so I will only briefly touch on what this circuit has the capability of doing. In the context of the 555 timers, astable mode refers to one of the operational configurations where it functions as an oscillator. In this mode, the timer continuously switches between its high and low states, generating a square wave output. This is apparent as looking at the internal components of the 555 IC. The rise and fall of the capacitor as it gains and loses voltage causes the SR latch inside to switch between releasing a high and low output at a stable rate. The rate at which it flashes can be adjusted by either changing the resistors or turning the potentiometer, and can be modeled by the equation F equals 1.44 divided by R1 plus 2R2 multiplied by C, where C is the capacitor included and F is the frequency it flashes at. Moving to the right, the monostable 555 generates a single output pulse when triggered by an external input, such as a button press. When the button is pressed, the timer's output switches to a high for a predetermined time before returning to low. The duration of this high state is controlled by external resistors and capacitors. This 555 setup acts as a debouncer as it removes any potential voltage leaks from the button when the 2 metal plates inside the button bounce off of each other repeatedly. Lastly, a bistable 555 has 2 states, high and low, and it switches between them based on external triggers, with this being a slide switch. When a slide switch is used in a bistable 555 timer, flipping the switch can toggle the outputs between high and low, essentially acting like a flip-flop with no automatic return to the original states until the switch is flipped again. With the parts of the counter out of the way, it all comes together with the inclusion of 7 NAND gates wired in a specific way. The diagram highlights what the output will be determined on whether the PBNO or slide switch is used earlier in the circuit. The purple diagram shows that if the selected output is positive and the astable pulse is releasing a square wave, the outcome will always be resulting in a square wave. The green shows a situation where the select switch is negative, resulting in a situation where, depending on whether the manual timer is positive or negative, the output will follow. The last potential outcome, illustrated in red, shows that if the halt line, no 555 timer needed, just a line pulled high or low, were to be pulled positive, the output will always be 0 no matter the value of the astable pulse, select output, and manual output. The halt line is built with a slide switch and a red LED to highlight if it is on. However, it can be left tied to a negative rail with no LED inclusion. Looking at the counter aspect of this specific project, the counter in a CHUMP computer increments the address and memory for each instruction cycle, keeping track of the next instruction to execute. It ensures the program runs sequentially unless a branch or jump occurs, as it is created through the use of a 74 LS161 AN chip, also known as a 4-bit synchronous binary counter. The chip is very similar to Project's 1.3 decade counter, except has a few key differences. Pin 9 on the 74LS161 chip is key as it is the load pin, something not seen on the 4017 decade counter. When the load pin is left high, the outputs will increment after each clock pulse. However, if pulled low, the outputs will instead match the 4 inputs, pins 3 through 6, values obtained by the 4 slide switch. This is key as it allows you to do something called branching in low-level assembly. Pin 1 is the clear pin, which allows you to clear whatever value is being stored and is wired to a PBNO in this project, while the clock output, the output of the 3 555s, after being fed through the 7 NAND gates, is then attached to pin 2. This allows for the output of the 74 LS161 chip to match whatever is being altered with the 555s. If the slide switch is flipped one way, the output will count with the square waves. If it is flipped the other way, it will match however fast the PBNO is pressed. Thank you for taking the time to watch my video on the RSGC CHUMP clock encounter.